In this screencast, we're going to review the Spring 2014 Exam 2 for Organic Chemistry 1. So we'll go ahead and get started. Question 1 says, what term best describes an aqueous solution where pH is less than 7? So the choices are neutral, acidic, basic, or can't be determined from the information. So in the pH scale, we're looking at basically 0 to 14, and the midway of that obviously is 7, and so 7 is neutral. Things between 0 and 7 are acidic, and 7 to 14 are basic. So the answer to this question is acidic, B. So given the following 4 molecules, rank them in order of increasing acidity. So one good strategy for answering any type of problem that gives you a name is just to draw the structure so you have a better idea of what you're looking at. So let's go ahead and do that first. We have 2,2,2-trifluoroethanoic acid. So here's ethanoic acid, here's the 1 carbon, here's the 2 carbon, and that's bearing 3 fluorines. We have ethanol. We have 2,2,2-trifluoroethanol. So again, let's draw ethanol. There's the 1 carbon, there's the 2 carbon. So we have fluorine, fluorine, fluorine. And then finally we have ethanoic acid. So if you look, you have alcohols and carboxylic acids. So the pKa's of these acids are typically greater acidities than alcohols. So what does that mean? The pKa of an acid is typically about 5. For an alcohol, it's around 15. So right there we can sort of segregate these, and this question is asking you to rank them in order of increasing acidity. So that means the alcohols are going to be listed first in the answers. So let's go ahead and write the Roman numerals as they're listed. So in terms of the answer, we're looking for 2 and 3 to come before before 1 and 4. So that can sort of help us eliminate some answers. So if you see 1 or 4 is the first choice, you can go ahead and eliminate that. So looking at A and B, those list the acids. Again, we're going in an increasing acidity, so the alcohols have to be first. That leaves us with C, D, and E. So the difference between 2 and 3 are these fluorine groups, and fluorine actually increases the acidity due to inductive effects. And basically what that means is all these electronegative fluorine groups tug through the sigma bonds, and that's what I'm drawing through these bonds now. That's what these arrows on the bond mean. So in comparing 2 and 3, 2 is going to be less acidic than 3 due to induction. So now if we look at the remaining choices, it looks like C is going to be the correct answer for this one based on elimination. So we need 2 to come first, so D doesn't have that. E has that, but it's saying that 2 is less than 4, and we know that 1 and 4 have to be the last 2 in the order. So that's going to be the first part of that. And so we use the same sort of logic to compare 1 and 4, and we can say that 4 is going to be less acidic than 1 based on that induction argument. So these are all electronegative. And again, they're pulling electron density through the sigma bond, as I've shown in those arrows. And so once you do that, you're ionizing the OH bond even more, making it more acidic. So C is the correct answer here. So 3, an acid strength in a solvent is defined by, and this one is the extent of ionization. So consider an acid, HA, and it's ionizing into proton and the conjugate base of that acid, so A minus. So the main thing is the extent of the ionization. It's not due to concentration, so we're talking about strength now, and strength is how much of this is formed, and so that's irrelevant of concentration. It doesn't have anything to do with polarizability, hydrogen bonding, or intermolecular forces. Question 4, consider a reaction that has reached equilibrium and favors the reactants. So the choices show up on the next page here. The reaction arrow would lie to the blank, and the Keq would be a blank number. So let's go ahead and write down an equation and look at these choices. So let's consider the following reaction: A plus B going to C plus D. And the question states that the reactants are favored. So meaning at equilibrium, the arrows would look like that. So we're favoring A plus B. So it's asking about the reaction arrow. So the reaction arrow is lying to the left, so we can eliminate A and C. Now we have to consider what is the Keq equation. And again, it's always the concentration of the products over the reactants. And we're saying that this number here, the denominator is large. So if you have C times D divided by A times B, which is a large number, you're going to end up with Keq being a small number. So the correct answer for this one is going to be D. So considering all the information given, cyclohexanol is blank then phenol. So you have a couple choices here, and let's go ahead and write some information down for this reaction. Phenol is going to be an acid. We have an acidic proton. We have an O minus charge, which I've highlighted. That's going to be a base. So this is a proton transfer reaction. So we have cyclohexanol, which is the conjugate acid, and then phenoxide, which is the conjugate base. And it's telling us that the Keq for this is 10 to the 5. That is a big number. And notice this arrow is pointing to the right. So it's saying cyclohexanol is blank than phenol. Is it less acidic, more acidic, or equally acidic, or no answer could be given? They're not equally acidic because then the equilibrium arrows would essentially be equal. And it's not more acidic because remember that the equilibrium lies towards the weaker acid-base pair. So the right answer for this one's going to be A. So again, the fact that the arrow is pointing this way and this is a large number means that we're pointing towards the weaker acid, which is cyclohexanol. So pKa-wise, phenols are about 10, and cyclohexanol, which is your typical alcohol, is about 16. So again, that's a lower number in terms of pKa. So that's going to be less acidic. So moving on to question 6. Acid A has a pKa of equal to 4. Acid B has a pKa equal to 7. Compound B is blank, then compound A. The thing that you have to remember about pKa units, so pKa is a log scale, so any difference between things are basically 10 to that power. So the difference between B and A is 10 to the 3. So compound B is going to be 1,000 times less acidic than compound A. So the correct answer for this is D. Again, this is the weaker acid. So 7 minus 4 is 3, and based on the log scale, you take 10 to the 3. That equals 1,000, so it's 1,000 times weaker. Which of the following statements best describes the relationship between the acidity constant Ka and pK in relation to the strength of the acid? Let's just go ahead and review the general equation for an acid ionizing. Ha ionizing to proton plus the conjugate base. Ka is equal to the concentration of the proton times the concentration of the conjugate base divided by the concentration of Ha. And again, pKa is equal to the negative log of the Ka. So here we have our choices. Strong acids have a small Ka and a large pKa. So a strong acid is going to favor the products, and that's going to mean that Ka is going to be a large number. So we can eliminate A based on strong and this being small, so that's not correct. B, weak acids have a large Ka, so that's not true. A weak acid is going to have a small Ka because the concentration of Ha is going to be higher, so meaning that this number will be very large and therefore Ka will be small. So again, we don't have the proper alignment of terms here. C says strong acids have a large Ka and a small pKa. So if you have a large Ka, that means the numerator is a very big number. When you take a very big number, the negative log of that, your pKa is going to be small. So C is actually the correct answer. So D, weak acids have small Ka and small pKa. Well, so that's not true. So the weak acids will have a small Ka, but they'll have a large pKa. So D is not correct either. So we're on to 8. Given the following group of C4 acids, rank their conjugate bases in order of decreasing basicity. So pay attention to what we're asking here. So it's giving you acids. So C4 means there's 4 carbons in the chain. And so you have to look at the pKa values for the acids, draw the conjugate bases, and then you want to put them in decreasing order. So let's go ahead and draw these things out. So we have butylamine. That was compound 1. We have butyne. That's compound 2. We have butanol. 2-butanol. It's compound 3. and we have butane, which is compound 4. So what are the pKa values from the table? So I'm going to write those in blue. For an amine, this is 38. An alkyne is 25. An alcohol is 16. And an alkane is 50. So what are the conjugate bases look like? So each of these is going to bear a negative charge now because we've removed a proton and we're forming the base. So remember that there's an inverse correlation between acid strength and base strength. So we're going to rank these now. So the weakest acid forms the strongest base, so this is going to be 1. Then the next is going to be the butylamine is 2, the alkyne is 3, and the alcohol is 4. So when we look at our answers, we have to correlate the rank with that number. So we're looking for 4 to be in the 1 position, so we eliminate A, B, and D. Now we're looking for Roman numeral 1 to be in the 2 position. So between C and E, we find that C is the correct answer. We can eliminate E. So moving on to question 9. Which of the following arrow-pushing formalisms best depicts the protonation of a secondary amine with hydrochloric acid? So you're looking for how does this base, which must be a secondary amine. A secondary amine is one that has 2 carbons and 1 hydrogen with HCl. So if you look at A, if we had to classify this amine, A would be a primary amine. It has 1 carbon group. B is a tertiary amine. It has 3. C is a secondary amine. It has 2. And D is a secondary amine. It has 2 as well. So we can eliminate A and B. Now we're left with C and D. C is incorrect because it's leaving out an arrow. Basically, if you're abstracting a proton, you have to have a bond forming and a bond breaking, which C does not. So D is the correct answer. So question 10 is asking, rank the following compounds from least acidic to most acidic. So this is basically a functional group pKa question. Let's identify the functional groups first. So our functional groups, we have an amine, we have an alcohol, we have a sulfonic acid, we have an alkyne, and we have an alkane. So you'll look on your your pKa table, you'd find that an amine is 38, alcohol is about 16, sulfonic acid, -12, alkyne, 25, and alkane, 50. So it says, rank the following compounds from least acidic to most acidic. So in terms of how you would rank these, this is going to be the least. We're given 5 compounds here. This is going to be the most, and then you're just tracking in terms of the pKa. So we have 5 is less than. So the next one would be 2 here, 3, 4. So in terms of the Roman numeral ranking, it would be 5 is less than 1, is less than 4, is less than 2, is less than 3. So we have to look at the choices here, and it's going to turn out that B is the correct choice for this. Again, we needed 5 is the least, so we can eliminate A and C. Then going through, 3 had to be the last, so we can eliminate D from there. And then it's really a choice between B and E. Yeah, and that's where you need to look at the Pka values and rank them accordingly. So question 11 says, what is the name that best fits the following alcohol? So you know it's an alcohol is the main functional group. So we need to identify the longest carbon chain. So I'm going to start down here in this part of the molecule and call this carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. So C9, nonane, you know it's an alcohol. That alcohol is at the 3 position. So we're going to identify at 3 nonanol. So again, that 3 is telling you where that alcohol is. So sort of right there, you can then look at your choices and eliminate B and C. So A and D both end with 3 nonanol. Now we're going to circle the longest chain. Go ahead and do that in blue. So everything outside that is a substituent. So we can see at positions 2 and 7 we have methyl groups. There are 3 of them. So we would have to say 2, 7, 7 trimethyl. At position 5 we have what's called an isopropyl group. So there's 3 carbons, it's a propyl, it's bonded to the second one, so that's isopropyl. And then we're gonna fit all that together into one name according to alphabetical order. And as we look at our choices, we're gonna see that D is the correct choice. A is actually missing a 2-methyl group. So it says a molecule named 5-bromo, 5-chloro, 3-cyclopropyl hexene has blank degrees of unsaturation. So you basically need to draw out the structure from this name, and then you can visually inspect for degrees of unsaturation. So we interpret this, we have hexene. So right there, that's telling us it's an alkene. That's going to be 1 degree of unsaturation. So let's draw. There's 6 carbons. The alkene starts at position 1 because it's not specified. If it's not specified, it has to start at 1. So we go along this chain, let's number it. 1, 2, 3, 4, 5, 6. Carbon 3 has a cyclopropyl group. That's a ring. That's equal to 1 degree of unsaturation. Carbon 5 has bromo. And chloro. So we have 2. The correct answer is going to be A. 13 says, how many degrees of unsaturation does a molecule with a molecular formula C10H17N2NO2 have? So the thing that should raise a question to you is this odd number of hydrogens. Again, we're always going to use CnH2n plus 2, and so we can't have an odd number of hydrogens. So what is the difference with this? For every nitrogen in the molecule, you subtract a hydrogen. So what we're going to end up with is, instead of C10H17, it will be C10H16 is what we use. And oxygen neither adds nor subtracts to the hydrogen count. So for N equals 10 carbons, we plug that in, C10H 2 times 10 plus 2. So we get H22. We have C10 H16. That gives us H6. And we need to divide that by H2. So we're going to get 3 degrees of unsaturation. So this answer is C. So 14 says, consider the rotation about the central C2C3 bond in 2-methylbutane. Rank the following conformations from lowest energy to highest energy. So obviously, if you look at these, the first thing I would do is just write what conformation they are. So this is eclipsed. This is staggered. This is staggered. And this is eclipsed. So what you can say immediately is that staggered conformations are lower in energy than eclipsed. So 2 and 3 must be less than 1 and 4. So this question is actually asking you sort of in that order, lowest to highest. So in the order, 2 and 3 must always be less than 1 and 4. So now we need to apply a little bit more knowledge to actually get this right. So let's look at the staggered conformations, 2 and 3. So in the blue pen here, what we have here and here are 2 gauche interactions, and we know those are worth 3.8. So we have 2 of those. That's going to give us 7.6 kilojoules per mole. In 3, we only have 1, so that's 3.8 kilojoules per mole. So we're working through the order here. We know that now in a revised ranking, 3 must be less than 2. So let's go ahead and look at our answer choices. So we can eliminate B, C, and D so far. So we're looking at choosing between A and E. And we know that 3 must be less than 2 in that order. E does not meet that criteria, so the correct answer for this has to be A. Then just to prove that, the other 2, what are their energy conformations? So we have an HH eclipsing, that's worth 4. CH3 H eclipsing, that's worth 6. Methyl-methyl is worth 11. So this is worth 21 kilojoules per mole. Here we have basically all of the same type of eclipsing, H-methyl. So that's 3 times 6 is 18 kilojoules per mole. So basically, conformer 1 has to be last in that order as the highest energy. 15 says, how many hydrogen-hydrogen diaxyl interactions are there in cis 4-tert-butyl-1-bromocyclohexane? So you definitely have to draw this one out or make a model of it to understand how you would figure that out. So here's our cyclohexane. So you're 1 in 4 substituted. So let me go ahead and number just so we can see 1, 2, 3, 4, 5, 6. Now if I draw this bromine, say I want to draw it on the bottom face, I know that at the 4 position the tert-butyl group has to be cis, so it's also going to be on the bottom face. However, we can't answer this question just yet because we have this large tert-butyl group at position 4 here. It's currently axial, so that's not going to be the most stable conformation. So this thing is actually going to do a ring flip to a more stable conformation where the tert-butyl group is equatorial and the bromine is axial. So what does that look like after we ring flip? Again, both of them are still on the bottom face. They're cis. The large group is now equatorial, which it has to be if we're looking at the most stable conformation. Now what we're going to do, we'll look at the top face of the molecule first. We have axial hydrogen, axial hydrogen. So there's 1. Again, we're looking at hydrogen-hydrogen diaxial interactions. Here's an axial hydrogen. There's 2. There's 3 on the top face, so let's keep track, 3 there. Now on the bottom face you have hydrogen here, and you only have another one here, so that's an additional 1. So the correct answer for this is C, which is 4. Question 16 asks, which Newman projection best represents looking down the C2-C3 bond of the following molecule? So in the Newman projection, again, the front carbon sort of has this peace sign or Y shape to it. The rear carbon is obscured by the circle, and so the bonds are emanating from it. When you look at this molecule, this OH group has to be on the right side. So we can eliminate A because it's on the left, and we can eliminate C because it's showing the OH group on the rear carbon. Or excuse me, it's in C we're looking down. C is actually looking down this bond. Excuse me. In either event, C is looking down the incorrect bond. So that leaves us with B and D to choose from. So the front carbon of each of those is the same, as you can see. The OH is going off to the correct side. Then you have the H and then the CH3 going down. So if you look at the original molecule, I'm going to circle the OH. The OH, they're on the same side. So if you sort of draw your eye here, this is an H, so that can't be correct. So here, this OH sees that OH. They're on sort of the gauche to one another. So D is going to be the correct answer for that one. So 17, which of the following chair flips is correct? This is where you really have to make sure that you're paying attention to the subtleties of the chemical communication. So in A, the left chair is cis, the right is trans. So that's not correct. So in answer B, they really did not do a chair flip here. this was a 180-degree rotation, so it's actually pretty much the same molecule. There's no chair flip has occurred. C, you have a 1-2 relationship, so 1, 2, it's cis. You have CH3 group equatorial, it flips to axial. Now you have OH group axial, it flips to equatorial. So that seems like it could be correct, but let's go ahead and look at D. D is not correct because you have a 1, 2, 3 relationship going to a 1, 2, 3, 4 relationship. So don't fall for cheap tricks like that. C is the correct answer. 18 says an organic molecule containing 2 rings, 3 double bonds, and 1 triple bond has blank degrees of unsaturation. So this is 2. This is 3. A triple bond has 2 pi bonds, so that's 2. So you add that all up, you get 7. So that one's pretty straightforward. So the molecule below contains which functional groups? So let's outline these in red, or in blue, excuse me. You have an acid, you have some alcohols, you have an amide. So that's what we're looking for in the choices here. So you do not have an aldehyde, you do not have a ketone, you do not have an ether, you do not have a nitrile, so the correct answer for this one is E. So which convention best represents the molecule 2,2-bromo-3-chlorobutanol? So there's actually a mistake in this. This should be 2,2-dibromo. So let's go ahead and, when you're given a name, draw it out yourself, and then you can compare it to the answers. We have butanol. That's a C4 aldehyde. 1, 2, 3, 4. 3-chloro. 2,2-dibromo. A is not correct. If you count the carbons, you have 1, 2, 3, 4, 5 carbons. We need a 4-carbon chain. Let's look at B, 1, 2, 3, 4. So this is 2-chloro, 3,3-dibromo, so that's not correct. What about C? You have 1, 2, 3 carbons. That's not correct. So it's got to be D. So basically, if you count these carbons, this is the aldehyde 1, carbon 2 in the back, carbon 3 in the front, carbon 4. So the 2 bromines are on the rear carbon, 2,2-dibromo, and then carbon 3 has the chlorine. So that's been a review of the spring 2014 CHE 255 exam 2 on acidity, nomenclature, and conformational analysis.